So the first thing when we're trying to graph a function is going to be to identify the domain or the interval of interest where we're going to graph. On what interval should the function be graphed, and if it's all the real numbers or not. Then after that, we're going to check for symmetry. We can exploit symmetry and takes advantage of that. For example, if the function is even, then the behavior is going to be the same on the right side of the y-axis than in the left side. If we have asymmetry, then we know that it's going to reflect the behavior. So in this case, f of minus x is going to be minus f of x, and you will see some sort of reflection going on with the graph. After that, or after making this consideration, we can find the first and second derivative of the function. Those are needed for finding the stream values, concavity, inflection points, intervals of increase and decrease, computing derivatives, particularly the second derivative as well. Might not be so practical in some cases. So some function might need to be graphed without complete derivatives, just the first one at least. Then after that, we're going to find critical points and possible inflection points. Remember, we're going to try to guess what the local streama are, and for that we get the critical points, which is where f prime is equal to 0, or f prime is undefined or do not exist. And then we have candidates to inflection points that are where f2 prime is equal to 0 or f2 prime is undefined. Then after that, we're going to find the intervals where the function is increasing and decreasing with the first derivative, and concave up, concave down with the second derivative. We're going to identify the stream values, so the maximum and the minimum. Whether it is with the first or the second derivative test, we're going to classify the critical points as local maximum, local minimum, or absolute maximum, absolute minimums. And using the second derivative, we're going to find out who the inflection points are. Then after that, we're going to check for possible asymptotes. So we're going to locate all vertical or horizontal asymptotes and determine the behavior. Remember, vertical asymptotes are going to occur in series of the denominator or problems at the domain of the function. And horizontal asymptotes require that you take the limit when x goes to infinity or minus infinity to check if the function is going to go to a particular number. If we have a rational function, we might have slant asymptotes that occurs with rational functions which the numerator is one more degree than the denominator. Finally, it's always important to do intercepts in the graph so we can check where the graph is crossing x equals 0 or y equals 0. And we can always use a couple points as well to graph our functions. So now let's go for some examples. Given the following information about the first and the second derivative of a function that is continuous on R, let's summarize the information using a number line or a real line and sketch the possible graph of that. So first, notice that we get that f prime is less than 0, or f prime is negative, and f2 prime is positive, and minus infinity to 0. Notice that that's saying a lot of things. This is saying in minus infinity to 0, the function is decreasing, but at the same time is also concave up. Okay. Now, if we go from 0 to 1, then this is saying, hey, in 0 to 1 now, f prime is positive and f2 prime is positive. So we still have concavity up, but now we have that the function is increasing. So 0, notice that 0 is changing from being decreasing to increasing, so likely this is going to be a minimum, and that is pretty much certified by the fact that the second derivative is concave up. So that's a good indicator of that. In the interval 1 to 2, notice that we have f prime is bigger than 0 and f2 prime is less than 0. So notice that this is telling me, hey, we're still increasing in here, but we're changing concavity. Now concavity is going to be concave down. Notice that 1 is likely going to be an inflection point, since there is a change on the concavity here from being concave up to concave down. Then later, if we go to the interval between 2 and 3, we have that f prime is negative and f2 prime is negative as well. So notice that there is no change in the concavity. So 2 is not going to be an inflection point, but there is a change between the increasing and decreasing behavior. In 1 and 2, we have that the function changes to be increasing to be decreasing. So it's very likely that 2 is going to be a maximum. And that is also certified by the fact that f2 prime is negative, so it's concave down. So we have that situation going on in there. So let's see a little bit of the summary of how things are going on. So notice that f prime less than 0 and f2 prime bigger than 0 gives me decreasing concave up on this interval minus infinity to 0. Then 0 to 1 is going to have reflect this behavior, which is increasing in concave up. Then in 1 to 2 we have increasing in concave down. In 2 to 3 we have increasing decreasing in concave down. So as expected, 0 is a local minimum, 2 is a local maximum, 1 is an inflection point, and then we're going to have a repeat of the behavior in 3 for inflection point. Notice that there's a change in the second derivative from being negative to being positive. So we have an inflection point in there. And then later in 4, we have a change from the function from being negative, decreasing, to being positive in the derivative. So we have the behavior of a local min, decreasing and then increasing. And this is certified by the second derivative that is telling me, hey, this is concave up around, so this is a local minimum. So now this chart that I have here with the behavior is only telling me the behavior of the function. It's telling me where the local minimum is located, and it's telling me whether the function is growing. However, I still need to use a Cartesian plane to translate that. So let's actually go ahead and define a function that might behave like that. Notice this function here is a local minimum in 0, is a local maximum in 2, and a local minimum in 4. It has change of concavity in 1, change of concavity in 3. So this pretty much matches this. Now I don't have exactly information about the function, but this is something that tells me the information of how the function is. Notice that I can certify that the behavior is going to be like this from the slope of the tangent lines. Now where the points are going to be exactly depends of pretty much if I have any information on the cuts with the axis. So for example, this cut with the y-axis and this cut with the x-axis here and here. If I have that information, then I should be able to complete my graph. So now let's take a look at an example of that, but within a specific function. We're going to use this graph guidelines that we just introduced to graph the function f of x equals x cubed over 3 minus 400x on its domain. So now the domain of this is the real number. This is a polynomial, so this is going to be on the real numbers. Because these are odd powers, this is an odd function, so we have some sort of symmetry with respect to the origin, but what happens on one side is going to be reflected in shift with respect to the x-axis on the other side. Now, the derivative of this are x squared minus 400 into x. So likely solving f prime of x equals 0, we're going to find out that x equals plus or minus 20. And for the candidates to inflection points, we have that f2 prime of x equals 0 yields x equals 0. So that's our possible inflection point. So now we get to say, we get to check intervals. We get to check what happens from minus infinity to minus 20, from minus 20 to 20, and from 20 to infinity in terms of maximum and minimums. And we gotta check if there's a change of concavity at 0. Notice that f prime can be factored as x minus 20 times x plus 20. So solving that inequality, we're going to have that f prime of x is less than 0 on the interval minus 20 to 20. Okay? And on the other hand, it's going to be positive, f prime of x is going to be positive on the minus infinity to minus 20 and 20 to infinity. Remember, we split a real line like this, and then we check with a point what the behavior is in there. So in this point, we can take like minus 30, and if we take minus 30 in here, we can verify that the sign is negative. In the same way, positive, sorry. In the same way, if I take like 0, we're going to actually get the negative value here. And if we take a larger number than 20, we're going to get a positive number here as well. So from the first derivative test, we can see this behavior increases, decreases, increases. And so that's increases and then decreases means that minus 20 is a local maximum. And for the fact that it decreases and then increases, x equals 20, then it's going to be a local minimum. Now for f2 prime, things are a little bit easier since I kind of can check right away with the numbers. For the negatives, this is going to be negatives, and for the positives, this is going to be positive. So it's going to be concave down on the negative side, and it's going to be concave up on the positive side. So this can be reflected as this. Notice there is a change in concavity at 0. So this is an inflection point, and I know that there is a change in the concavity there from concave down to concave up. So it's doing something like this. And we can summarize that behavior as something like this here. We have the local maximum here, inflection point, and then we have the local minimum here going on. So using that information, we graph some extra points. If you plug in 0, you're going to get that this is a 0. And if you factor 1x, you're going to find out that in 30 point something, you're going to have some zeros. And so you can graph this 0 and this 0. You can get the information of what is the maximum, what is the minimum. And with that, once that you know, since you know this is a maximum, this is a minimum, and there's an inflection point here crossing, then it's very easy to produce this graph.